Pluto is a faraway and perplexing minor planet. Once a singular member of our planetary family, ceaseless, unsettling revelations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a staggering disclosure. They proposed that this chilly world is on a collision course with Neptune. But how could this happen, and what might be the consequences of such a monumental event? Are we witnessing a flooring effect or mere unpredictability? Or is there more to this potential cosmic collision? Join us as we explore the possible outcomes of a Pluto-Neptune crash. Pluto, a former planet that was downgraded to a dwarf planet, is significant due to its peculiar orbit. It remains a subject of interest and study within the scientific community. According to recent hypotheses by leading experts, Pluto's orbit is perilously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising alarms about a potentially catastrophic collision between these two planets, which could pose a massive risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. But the intrigue doesn't stop there. Pluto's orbit is characterized by its unusual elliptical shape, straying far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is significantly more extreme compared to the other planets. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying expectations based on their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers sought to determine its unique trajectory. Unlike other planets whose orbits lie close to the ecliptic plane, Pluto's orbit stood out due to its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. Despite these complexities, Pluto's orbit has remained stable over long periods, preventing a collision. This stability is due to the intricate interplay of gravitational forces, particularly from the giant planets like Neptune, Jupiter, and Saturn. Jupiter's immense gravity is strong enough to keep Pluto on a consistent path for potentially billions of years. These factors are crucial in maintaining order and preventing chaos in our solar system. Pluto's orbit is a remarkable example of celestial mechanics at work, demonstrating both stability and disruption in our cosmic neighborhood. The unique characteristics of its orbit, influenced by the gravitational forces of nearby planets, especially Neptune, highlight the complex and dynamic nature of space. Predicting significant events, especially involving erratic orbits like Pluto's, presents major challenges. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainty. While mathematical simulations provide a robust means to understand and foresee the future behavior of celestial bodies, they also reveal the limits of our predictive capabilities. So why are renowned astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune? Despite the complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both prominent figures in cosmology, have expressed concern about a possible crash between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a stunning and catastrophic event in our solar system. The impact would release an enormous amount of energy, likely obliterating Pluto due to its smaller size and icy composition. Debris from the collision could spread across the nearby solar system, posing risks to other planets and their moons. For Neptune, such an impact could alter its current environment and potentially even its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory, offers a fascinating perspective on the potential impact. His insights into the future of space exploration and the relationship between celestial mechanics and theoretical physics provide valuable understanding of the phenomena surrounding Pluto's orbit. Understanding the intricate gravitational interactions and orbital mechanics of celestial bodies like Pluto could yield crucial information for future space missions. This knowledge could aid in exploring the solar system more effectively, anticipating potential threats, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a guide for how we might approach and understand distant worlds. In planetary science, celestial mechanics, and theoretical physics, these fields are deeply interconnected. The movement and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to fundamental principles of physics. If Pluto and Neptune were to collide, it would be a spectacular event in cosmology, offering an extraordinary observational opportunity that could potentially tie into string theory. String theory, a theoretical framework where point-like particles in particle physics are replaced by one-dimensional strings, seeks to explain the fundamental forces of matter and the universe. The impact might create extreme conditions of energy and gravity, potentially leading to environments where predictions made by string theory could become observable. For instance, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, which is a key area of interest in string theory. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be immense. It might contribute to our understanding of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's peculiar dance around the Sun continues to captivate scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its reclassification as a dwarf planet sparked debate and reshaped our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in astronomy, have raised concerns about a potential collision between Pluto and Neptune, shedding light on the intricate forces at play in our cosmic neighborhood. Their warnings underscore the importance of understanding the gravitational interactions and orbital mechanics that govern the movements of celestial bodies. Pluto's orbit, marked by its eccentricity and steep inclination, defies traditional assumptions and challenges our perspective on planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path takes a unique course, crossing Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over many years. Despite the chaotic nature of its trajectory, Pluto's orbit remains relatively stable within the broader context of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as suggested by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and unpredictability in planetary dynamics. While such an event remains speculative and highly unlikely in the near term, the gravitational dance between Pluto and Neptune emphasizes the delicate balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided stunning images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed remarkable details about Pluto's surface features, including vast plains of water ice and wide expanses of frozen nitrogen, enriching our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaborative efforts essential for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer reaches of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, helping us understand planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific taxonomy and the evolving nature of astronomical knowledge. While Pluto meets several criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Embracing Pluto's orbit broadens our understanding of celestial mechanics and planetary dynamics, particularly in the outer regions of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists gain a deeper appreciation for the complex gravitational influences that govern the behavior of planets, dwarf planets, and their moons. Implications for future space missions. The insights gained from studying Pluto's unique orbit and interactions with Neptune extend far beyond academic interest. They provide critical information for planning future missions to explore the Kuiper Belt, the region of the solar system that contains Pluto and countless other icy bodies. This area remains largely unexplored, yet it holds clues about the early solar system's formation and evolution. Understanding the orbital mechanics of celestial bodies like Pluto is vital for navigating spacecraft safely through these distant regions. For example, the success of NASA's New Horizons mission demonstrated the importance of precise calculations and innovative technologies. Future missions may aim to study other trans-Neptunian objects, dwarf planets like Eris or Haumea, and even the mysterious Oort cloud, which lies even farther from the Sun. Scientific value of a hypothetical Pluto-Neptune collision. While the prospect of a Pluto-Neptune collision is exceedingly remote due to their stable orbital resonance, studying such a hypothetical scenario can still offer valuable insights. Computational models of such an event allow scientists to simulate the effects of high-energy impacts in the solar system. This could shed light on the formation of planetary rings. A collision could generate massive amounts of debris, potentially forming temporary rings around Neptune or even new moons. Gravitational effects on neighboring bodies. A disruption in Neptune's orbit could have ripple effects across the solar system, altering the trajectories of smaller objects in the Kuiper belt. Clues about planetary evolution. Observing collisions, even in simulations, can help scientists understand how planetary systems form and evolve over billions of years. Pluto's role in expanding the definition of planets. The debate over Pluto's planetary status remains a touchpoint in modern astronomy. When the International Astronomical Union, IAU, redefined the term planet in 2006, Pluto was reclassified as a dwarf planet due to its inability to clear its orbital neighborhood of other debris. This decision sparked controversy and inspired public campaigns advocating for Pluto's reinstatement as the ninth planet.